The following presentation demonstrates how controlled plasticity burnishing introduces beneficial residual stress to improve structural integrity and mitigate stress corrosion cracking in nuclear waste containment vessels. In 2003, the Yucca Mountain Nuclear Waste Repository discovered cracks in the heat-affected zones of closure welds on waste containment systems. When containers are welded shut, shrinkage during cooling can cause high tensile stresses, leaving the welds in tension. In a corrosive atmosphere, these conditions create the ideal environment for stress corrosion cracking, or SCC. Unaddressed cracks will continue to propagate, compromising the integrity of the containment system over time. Three things must be present for stress corrosion cracking to occur: a susceptible alloy, corrosive environment, and tensile stress exceeding the threshold for cracking. Eliminating any one of these will prevent SCC. Since simpler methods like coatings or changing the alloy had not proven effective, mitigating tensile stresses became the goal of the Yucca Mountain project. When evaluating various surface treatment options, the Yucca Mountain team considered factors such as environmental complexity, material behavior, and the need for a long-term, maintenance-free solution. Controlled plasticity burnishing and laser shock peening emerged as the leading contenders. Trials were performed on welded alloy 22 plates designed to mimic the behavior of the waste container closure welds. Plates were treated with CPB and LSP, respectively. CPB is a similar process to low plasticity burnishing, with the main distinction being the amount of imparted cold work. Unlike coatings or alloy selection, these processes strengthen the corrosion-resistant material itself by imparting a deep, stable layer of compressive residual stress. As such, the solution is permanent and requires no reapplication. Residual stress measurements were performed on the treated plates. The CPB treated plates achieved significantly deeper compression at 12 millimeters, well beyond the depth required to eliminate the risk of crack propagation from SCC. The graph shown here is a comparison of CPB and LSP to a depth of 6 millimeters for ease of presentation. Superior performance and the lower cost of implementation ultimately led to CPB being chosen for the Yucca Mountain work. Lambda developed a dual CPB system designed for integration with robotic positioning and welding systems at Idaho National Labs. INL staff reported flawless performance with 100% processing documentation and repeatable results. This solution ensured the closure welds would remain free of SCC for at least 50,000 years, 5 times longer than the originally designed lifespan of the containers. Though the Yucca Mountain project was ultimately defunded due to political and environmental concerns, the successes and insights gained from this project continue to shape future nuclear waste storage strategies. The same benefits that made CPB ideal for Yucca Mountain apply today. Controlled plasticity burnishing and LPB deliver long-term reliability with minimal downtime, adaptability to new and legacy systems, and proven failure prevention. These points are becoming more important as the requirement for reliable power grows. The International Atomic Energy Agency projects a 40% increase in nuclear generation by 2050, driven by the demand for clean energy and data centers. Technologies like CPB and LPB ensure that long-term waste storage keeps pace with this growth, protecting the environment and building public confidence in nuclear power's future. For more information or to discuss your application, visit our website or contact us at 513-561-0883.